The directions say to find dy dx. Let's take a look at example 1. Suppose we're given the parametric equations x equals t over 1 plus t and y equals the square root of 1 plus t. dx dt is equal to, by the quotient rule, 1 plus t times 1 minus t times 1 divided by 1 plus t raised to the second. Simplifying, we come up with 1 over 1 plus t raised to the second power. dy dt is equal to 1 over 2 times the square root of 1 plus t. dy dx is equal to dy dt divided by dx dt. So this is equal to 1 over 2 times the square root of 1 plus t divided by 1 over 1 plus t raised to the second. So dy dx is equal to 1 over 2 times the square root of 1 plus t times 1 plus t raised to the second divided by 1. Remember, when you divide by a fraction, you multiply by the reciprocal, and that's where we're getting this from. If I simplify, we end up with the following. dy dx is equal to 1 plus t raised to the 3 halves divided by 2. That's example 1. Let's take a look at example 2. Suppose we're given the parametric equations x equals t e to the t and y equals t plus sine of t. The same directions apply. We want to find dy dx. dx dt, by the product rule, is t e to the t plus 1 times e to the t. If I factor out the e to the t, I get dx dt is e to the t times the quantity t plus 1. dy dt is 1 plus cosine of t. dy dx is equal to dy dt divided by dx dt. So this is equal to 1 plus cosine of t divided by e to the t times the quantity t plus 1. That's example 2. The directions say to find dy dx and the second derivative of y with respect to x. For which values of t is the curve concave upward? In example 3, suppose we're given the parametric equations x equals t squared plus 1 and y equals t squared plus t. dx dt is equal to 2t and dy dt is equal to 2t plus 1. So dy dx is equal to dy dt divided by dx dt. So this is equal to 2t plus 1 divided by 2t. Now, let's take a look at the second derivative. The second derivative of y with respect to x is the derivative of dy dx with respect to x. So this is an important inequality right there. And we're going to do something very similar. So what I'm going to do is I'm going to take the derivative of dy dx with respect to t, that's the numerator up here, and divide by dx dt. Okay? So I claim that's the second derivative of y with respect to x. Now, if we come over here, we already know dx dt is equal to 2t. And so if I look at the derivative of dy dx with respect to t, that's the derivative of 2t plus 1 over 2t with respect to t. And then I applied the quotient rule. So this is equal to 2t times 2 minus the quantity 2t plus 1 times 2 divided by 2t raised to the second power. So the derivative of dy dx with respect to t ends up being negative 2 divided by 4t squared when it's all said and done. So I just simplified in order to get there. Notice how I distributed the 2 to each term within the parentheses. That's where I'm getting the 4t plus 2. And then I took 4t minus the quantity 4t plus 2. And I have to distribute the negative to each term within the parentheses. When I do that, the 4t ends up canceling, right? The 4t terms. And you're just left with negative 2. So that's where this comes from. If I put it together, it looks like the second derivative of y with respect to x is negative 2 over 4t squared divided by 2t. And you can think about this as 2t over 1. But this is negative 2 over 4t squared times 1 over 2t. 2's cancel, and we get the second derivative of y with respect to x is negative 1 over 4t raised to the third power. Now, the second derivative of y with respect to x is undefined when t equals 0. Now, let's go forward with this. Now, we're going to look at two intervals. We're going to look at the interval from negative infinity to 0, and we're going to look at the interval from 0 to infinity. And we're going to test a value in the interval negative infinity to 0. So I choose t equal negative 1. And the second derivative of y with respect to x evaluated at t equal negative 1. So notice if I replace t with negative 1, negative 1 to the third is negative 1. And negative divided by negative is a positive. And so notice how I get 1/4, and that's positive, okay? So think concave up on the interval negative infinity to 0. But you're still not off the hook because we still should test 0 to infinity to be complete. And we're going to test t equal to 1. The second derivative of y with respect to x evaluated at t equal 1 is negative 1/4, which is less than 0. So on this one, you want to think concave down because we got a negative number and hence concave down on the interval 0 to infinity. So what does that say? The curve is concave up on the interval negative infinity to 0. You can also say the curve is concave up when t is less than 0. So that says the same thing, essentially. Let's take a look at example 4. Suppose we're given x equals t minus the natural log of t and y equals t plus the natural log of t. The same directions. dx dt is 1 minus 1 over t. dy dt is 1 plus 1 over t. dy dx is equal to dy dt divided by dx dt, which is 1 plus 1 over t divided by 1 minus 1 over t. So I multiplied the numerator and denominator by t to clear the fraction. And when I do that, I'm going to distribute the t to each term within the parentheses. So the t in the numerator gets distributed to each term in the numerator. The t in the denominator gets distributed to each term in the denominator. And so dy dx, so we can write that here. dy dx ends up being t plus 1 divided by t minus 1. So it's a nice way to simplify. Now I want the second derivative of y with respect to x. But that's the derivative of dy dx with respect to x, which is the derivative of dy dx with respect to t divided by dx dt. Now, dx dt is 1 minus 1 over t. And I'm just going to simplify this. Remember, 1 is equal to t over t as long as t is not 0. And t over t minus 1 over t ends up being t minus 1 over t. And that's where we get dx dt, right here. Now, the derivative of dy dx with respect to t by the quotient rule is t minus 1 minus the quantity t plus 1 divided by t minus 1 raised to the second. And when I simplify that, I end up with negative 2 over t minus 1 raised to the second. So the second derivative of y with respect to x ends up being negative 2t divided by t minus 1 raised to the third. So the second derivative of y with respect to x is undefined when t equals 1, and the second derivative of y with respect to x is equal to 0 when t equals 0. We need to consider both. So we have an interval. We have the interval from negative infinity to 0, 0 to 1, and then 1 to infinity. And so, if anything, draw a number line. Okay. So here we have 0, and then we have 1. And you can see the intervals on the number line, right? So if I use blue here, I have the interval from 0 to 1, and when I make my parenthesis face to the right, I'm talking about the interval from 1 to infinity. And when I make my parenthesis over here face to the left, I'm talking about the interval from negative infinity to 0. You can see the intervals form on the number line. And so I'm going to test a point, if it helps, t equal negative 1, t equal 1/2, and t equal 2. And I'm going to plug those values of t into the second derivative and test them out. The second derivative of y with respect to x evaluated at t equal negative 1 is 2 over negative 8. The only thing I care about that number is that it's negative. And that's less than 0, and that makes the graph on the interval negative infinity to 0 will be concave down. That's what CD stands for, concave down. Or you can think this way. And if I look at the second derivative of y with respect to x, evaluated at t equal half, that's negative 1 over negative 1/2 to the third, and that is greater than 0. And so we're concave up on the interval 0 to 1. So you want to think that way. And then the second derivative of y with respect to x evaluated at t equal 2 is negative 4, which is less than 0. And so that's concave down. And so this curve is concave up on the interval 0 to 1. And that's how this problem works. Let's take a look at this on the next page. Suppose I ask you to find the points on the curve where the tangent is horizontal or vertical. Now I want to give you a problem here. Let's take a look at number 5, example 5. Suppose I had the parametric equations x equals t to the third minus 3t, and then y equals t squared minus 3. So we need dx dt. Well, dx dt is equal to 3t squared minus 3. dy dt is equal to 2t. Okay. to find the points on the curve where the tangent is horizontal, we're going to set dy dt equal to 0. And that's going to allow us to solve for t. Okay, so that's our first step. So in other words, if we go back, notice that dy dt is equal to 2t. So we're going to set 2t equal to 0. Solve for t, we get t equals 0. Now, we need x and y. Well, if I go back to the original parametric equations, I'm going to replace t with 0. So x is equal to 0 raised to the third minus 3 times 0, which is equal to 0. And then y, if we go back, is 0 squared minus 3. And that's negative 3. So the point is 0, negative 3. Now, to find the points on the curve where the tangent is vertical, would it be fair to say that I'm going to set dx dt equal to 0? Okay, so if we go back, dx dt is 3t squared minus 3. Okay, so therefore, 3t squared minus 3 is equal to 0. So that tells me t squared is 1. So t is plus or minus 1. And just like before, we need x and y. So if we go back, right, we're going to replace t with 1 and replace t with negative 1 in those parametric equations. So at t equal to 1, x equals 1 to the third minus 3 times 1, which is negative 2. And then y is 1 squared minus 3, which is negative 2. And then at t equal negative 1, x equals negative 1 to the third minus 3 times negative 1, which is 2. And then y is negative 1 to the second minus 3, which is negative 2. So the points are negative 2, negative 2, and 2, negative 2. So those points make the tangent, in this case, the tangent vertical. And then over here, the point 0, negative 3 makes the tangent horizontal. So, and that's going to do it for this video. This is on calculus with parametric equations, and we did 5 examples. Thank you.